Good morning everyone. My name is Shalini. Today in this video I am going to discuss about the crystal field theory. This topic is from the chapter coordination compound. This is called as CFT, crystal field theory. So after the completion of this video, you will be able to draw the CFT for both octahedral and tetrahedral complexes. So let us start our topic. As we know, the d orbitals. How many orbitals are present here? We have 5 orbitals in d orbit. This is 1, 2, 3, 4 and 5. If we name these orbits, this is dxy, this is dyz, dzx, dx square minus y square, dz square. Now, we will see these 5 orbitals have the same energy. These 5 orbitals have the same energy. So, these are also called as degenerated orbitals. What we call degenerated orbitals. Why do we call as degenerated orbitals? Because they have same energy. They have same energy. So, first of all, we have to see the structure of these orbitals. So, let us draw for dxy. Let us draw the structure for dxy orbital. Here we have the x-axis and the y-axis because the orbitals are present in between the x and y-axis. So, these are the lobes. Okay. These are present in between the axes of x and y. So, here how many lobes are there? This is 1, 2, 3 and 4. Here are 4 lobes. Similarly, we can draw for dyz. Here we have y-axis. This is z-axis. So, the lobes are present here in between the axes. And now we will draw for dzx. So, this is x-axis, z-axis, and the lobes are present in between the axes. In between the axes. Here we have 4 lobes. Again we have 4 lobes here. Now we have to draw for dx square minus y square and for dz square. So for dx square minus y square, we have to draw the structure. So here we have x-axis, y-axis because we have to draw for x and y. So here the lobes are present on the axis. This is different from these 3. The lobes are present on the axis. Here we have 4 lobes. Now we have to draw for dz square. So we have to draw the structure here. The shape of the orbital. This is z-axis and the lobes are present on the axis. So this is also different. Here the lobes are present on the axis and also one ring is present between them. One ring is present between them. So here we have how many lobes? See, this is 2 lobes here. These are 2 lobes and one ring. So here we have drawn the d orbitals shape, the orbitals of dxy, dyz, dzx. This is for dx square minus y square and this is for dz square. If we see, these orbitals are present in between the axis and these are present on the axis. So these are also called as axial orbitals. These are called axial orbitals. So axial orbitals are axial orbitals. What are axial orbitals? dx square minus y square and dz square. And now we see these orbitals are present in between the axes. So these are also called as, in terms of axial and non-axial, these are non-axial orbitals. So non-axial orbitals. These are dxy, dyz and dzx. So these are non-axial orbitals. So now let us take an idea about the crystal field theory. So according to this theory, the metal and the ligand attach with each other through electrostatic interaction. We know in the coordination compounds we have d block elements are present and the ligands approaches the metal and their bonding, and then the bonding establishes between them. So in the crystal field splitting theory we have the electrostatic interaction. We have the electrostatic interaction between the ligands and the metal. There is no covalent bonding. There is the attraction only between the ligands and the metal. So in this theory, the metal behave as positively charged center. The metal behave as positively charged center and the ligand, because they have the lone pairs of electron, so it behaves as the negatively charged center. So we have the d orbitals here of d block elements and we have the attraction with the ligands. So if you see, we have here octahedral ligands and also we can have the tetrahedral ligands. If we have the 6 ligands surrounded by the metal, if the 6 ligands are surrounded by the metal, so this is called as octahedral ligands, and if the 4 ligands is surrounding the metal, this is called as tetrahedral ligand. We also represent this as OH. This is for octahedral and this is TD. This is the short notation for tetrahedral ligand. So let us understand about the CFS, the crystal field splitting in octahedral complexes. So if you see, these are the d orbitals. First of all, we will see the splitting energy for octahedral. So we have these 5d orbitals. These are the orbitals of metal. This is 1, 2, 3, 4 and 5. These are named as dxy, dyz, dzx, dx square minus y square and dz square. These are the d orbitals. And when the ligands approaches the d orbital, the energy is somewhat increases. The energy is somewhat increases. When the d orbital feels that the ligand is approaching the metal, then the metal d orbitals feel the repulsion, and due to this repulsion the energy is somewhat increases. This is 1, 2, 3, 4 and 5. These orbitals increases the energy. So this is symmetrical effect. This is symmetrical effect of ligands. The energy is increases. Now, when the metals approaches completely, when the metal feels interaction between the ligands and the metal, the energy of the d orbitals is changed. These are the 3 orbitals, naming dxy, dzx, dyz and dzx. And this is dx square minus y square and dz square. So, when the ligands completely approached with the metal d orbital, the energy of the 2 orbital is slightly increases and the 3 orbitals slightly decreases. This is called as barycenter. This is called as barycenter. Barycenter. So, if you see above the barycenter, there are these dx square minus y square and dz square. So, these 2 orbitals whose energy is increasing, this is called as Eg orbitals. This is called as Eg orbital. And below the barycenter, there are 3 orbitals named as dxy, dyz and dzx. So, these all 3 orbitals are called T2G. This Eg and T2G you will study in your higher classes in the chapter in the topic group theory. So, this G is here, this is Z-rate orbitals. This is G-rate orbitals, and which have center of symmetry. This you will study in your higher classes, which have the center of symmetry. Only I am telling you about a little information about G here. What is G? Center of symmetry are called Zeroid orbital. Zeroid orbitals. For example, all s block elements and all d block elements are called zeroid orbital. S orbitals, s block elements and d block elements are called zeroid orbital. So you don't need to understand about the zeroid and unzeroid. Simply you have to see that below the very center we have the three orbitals which feel less repulsion. So their energy is decreasing, and the orbitals which feels more repulsion, these are called Eg orbitals which have the more energy. So these degenerated orbitals is splitted upon the when the ligand approaches the metal. These orbitals have the changes in their energies. So this is for the octahedral ligands. And if we see the energy from the very center, so there are three orbitals and the two orbitals have the higher energy. If we see the energy, the difference of the energy here, this is total orbitals, we have 5 here. So this is 5 and the two orbitals have the higher energy. So this is the difference between the barycenter and the T2G orbitals. So this is present below the barycenter, so we will put a minus sign here. So the energy here is 2 by 5 and this is for octahedral, so we will write as D delta naught. This is minus 2 by 5 delta naught. And here above the barycenter 3 upon 5 delta naught, and this is present above the barycenter, so the sign will be positive here. And if we resolve this, this will be plus 0.6 delta naught and this will be minus 0.4 delta naught. And the difference of these energies is called as this. The difference of their energies for between the Eg and the T2G orbital, these are called CFSE. The crystal field stabilizing energy. Also, this is crystal field splitting energy. So this complete representation of orbitals is for the octahedral ligands, when the 6 ligands are attached with the metal. So this is for octahedral ligands. Now we will draw for the tetrahedral ligands. So here this is splitting energy splitting of d orbitals for tetrahedral complexes. So what is tetrahedral complexes? When the 4 ligands approaches the D block elements. So this could also be represented as Ml4. So M here is metal, the central metal, and these 4 ligands approaches the metal. So now we will study about this tetrahedral splitting energy. So first of all, let us draw for the octahedral. Suppose this is for octahedral. We have not drawn the shape of octahedral here. So this is for octahedral OH. These are ligands. So these are the 6 ligands. So this can also be written as Ml6. M stands for metal and the 6 ligands approaches the metal. 6 ligands form bonding with the metal. So this is represented as Ml6. This is for octahedral. Now we have to draw for tetrahedral. So this is metal here and these are ligands. These are ligands. So this is for tetrahedral. Now we have to draw the splitting energy for tetrahedral complexes. Here also we have the orbitals. These are 5 orbitals. This is 1, 2, 3, 4 and this is 5. This is dxy, dyz, dzx, dx square minus y square, dz square. Again, when the metal feels that the ligand is approaching, their energy is somewhat increases. So these orbitals, these degenerated orbitals have the slightly increasing in the energy. This is 1, 2, 3, 4, 5. All these orbitals have the slightly increasing in their energy. So when the ligand completely approaches towards the metal, so their energy, the energy of 3 orbitals, for dxy, dyz and dzx increases, and the 2 orbitals have the decrease in the energies for dx square minus y square, dz square. In the octahedral complexes, we have written it as T2g orbital. But for the tetrahedral, we have to write here T2. We do not have to write here G. Simply, we will write here T2. And this is E. So, this is the representation for tetrahedral complexes. Again, all the values are same for the tetrahedral complexes. This is barycenter. This will be minus delta 3 by 5 delta H, and this will be plus 2 by 5 delta H, and this complete the difference between the energies of the orbitals is called CFSC. Again, it is called as CFSC, the crystal field splitting energy or crystal field stabilizing energy. So This complete representation is for octahedral and tetrahedral complexes. If we see the relation between the tetrahedral complexes, this is for T, tetrahedral complexes and octahedral complexes, this will be 4 upon 9 delta naught. This is the relation in between the tetrahedral and the octahedral energies. And for square planar delta SP, square planar shape, this will be 1.3 delta naught. If we see the energy difference, the unit of energy here, this will be in, if we see the unit of energy here, this can be joule, the standard unit, or it can be in centimeter inverse or in electron volt. So here we have seen the crystal field theory for octahedral and tetrahedral complexes.